Hi everyone, thanks for turning up, and it's great to see all of you here today. And today's presentation is by Berta Vilacís from the LMU University in Munich. But just before we get going, just go through the usual housekeeping slides. So the ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuous connection to these lands, water and culture, and pay our respects to the elders, past and present, and of the particular people whose land we're on, which are the Gadigal peoples of the Eora Nation. So first of all, a big thank you to all of our corporate members, without which our activities would not be possible. Our corporate members are shown on the screen here. And also a big thanks to the branch sponsors for all of the state and territory branches, which are also shown on the screen here. So a big thanks in particular to the NSW branch sponsors. So in July, our event was sponsored by Fender Geophysics, and in August, our monthly event was sponsored by Bridgeport Energy. So, these sponsorship really does help the ASEG conduct these events. It really is a great way to engage with the community. So if anybody would like to get involved in sponsoring our wonderful events, then please get in touch with either myself or with President Stephanie. So if anybody is joining us at the moment online, then regarding the questions and answers, please use the Q&A boxes, which you'll find on the ribbon at the top of your screens, and we will come to these questions at the end of the presentation. And just a little bit about some upcoming webinars which are being held by the ASEG. So on the 27th of September, we have a webinar by Maria Constanza Manacero, which is titled Including 3D Magnetotelluric, shows how much I know about that topic, data into joint probabilistic inversions for imaging the deep earth. And on the 6th of October, we have Dr. Michinori Asaka presenting on a predictive anisotropic rock physics model of shale and its practical applications. And then our upcoming meetings for the NSW branch are on the 19th of October, where we have Derek Palmer from UNSW speaking. On the 16th of November, we have our student night, where we will hear presentations from some students who have recently been granted scholarships by the ASEG New South Wales branch. And on the 7th of December, we have our dinner, and it says Fortune of War, which I know nothing about, but it sounds good. So yeah, but it sounds like it'll be good. If it's anything like last year's annual dinner, it will be very good. So. And just for those of you who are tuning in online, or for those of you who, I think everybody is a member here, but there are lots of benefits to becoming a member, which you can see on the screen here. So we always on the lookout for new members. And yeah, please keep in touch. So now just to introduce the speaker. So Berta Vilacís is a PhD student in geodynamics at the Ludwig Maximilians University of Munich. She did her bachelor in physics at the University of Barcelona and focused in applied seismology during her final year. At the same time, she completed a one-year fellowship at the Catalonia Seismic Network. After working in maintaining and processing data from the IEC Seismic Network in 2017, she moved to Munich, where she completed her PhD, so her MSc in geophysics in the joint program by TUM and LMU Munich. In 2019, Berta started her PhD in LMU Munich, and her research focuses on using geological information such as geological maps as a way to observe, map, and track past mantle convection. So without further ado, I'll hand over to Berta for her presentation.
Thank you. So let's, oops. Oh.
Can you put your hand up? Yes, yeah. Is that good?
Yeah, I'm now green.
Okay.
Okay.
It follows your route to follow you now. Yeah.
Awesome.
Good job you realized, otherwise it's a bit on me.
Okay, yeah, well, thank you very much for the invitation and for the kind introduction. Yeah, and what I want to start, it's very weird to see myself in the screen. Can I just, okay, should be fine, right? If you don't see me during the presentation, just let me know. Okay, so I want to start to give a very short overview of the structure of the Earth. Yeah, here we go. So we have mainly the core, the mantle, and the crust. And what I'm mainly focusing in my presentation is how the mantle and the crust interact. In the mantle, what we have is a process called convection, which is a movement of transport of mass. The bottom, so the core, is hot, and the crust is cold. So that creates movement upwards and downwards of cold and hot material. It's actually a similar process of what happens when you put a pot of water to boil. And if you can see in this image, the pot of water, the surface is not still. It varies depending where you have these bubbles of water rising up or down. So a similar process happens in the Earth's surface, and that's actually what I am studying, how this surface evolves through time. So what do we have in, like, we don't have a pot of water that we can open and see how it works. The Earth has a spherical geometry, and the composition of the mantle is mainly out of silicates, which creates, well, it's highly viscous, and that means that we have convection at geological timescales, which means millions of years. So very, very, very long time. But understanding such process as mantle convection is crucial to understand our knowledge of the Earth past. So what we can do is, because the mantle, how this mantle, so the mantle convection affects the surface of the Earth, and how it affects the surface of the Earth, it creates horizontal and vertical motion. The horizontal motion, usually it's shown as plate tectonics, so how plates move far away from each other or close to each other. This is can be one of the consequences. And vertical motion, it's shown as an uplift or subsidence of the surface. Uplift, it's when we have, for example, a positive buoyancy, or what we can call a plume, that rises through the mantle and it creates an uplift in the surface. And contrarily, a negative buoyancy, so what we can call a slap, creates a subsidence of the surface. As I said before, the mantle is highly viscous. So that means that the Reynolds numbers, it's very, very small. And that applies that when we look at the conservation of mass and momentum, the viscous forces surpasses the inertial forces. So we can take an approximation that's called the Stokes flow. And this gives a flow that's instantaneous and linear. Instantaneous means that at any given time, you can change the forces around, and the entire fluid or the entire geometry will know that something has changed, and there's an acquired balance from it. So that means that if we change a little bit, this will affect how the fluid will move. And with that means that if we want to have good mantle flow models, we must compute it in a global geometry. When we do it in another type of geometry, this will be highly affected by the surface of the boundary conditions, and the fluid will not be representative of the system that we want to study. A way to see how this how the surface expression changes throughout time it's using what we call the Earth model kernels. It's very complicated, but let's go a little bit through it. So this is what they call in seismology, they call the grain functions. They tell us, given a wavelength, what happens to the surface, to the different quantities that you see here, the geoid undulations, the gravity anomalies, or the surface topography. Because I'm focusing mainly in the surface topography, I'll just want you to focus on that. But what you can see is that changing the Earth parameters, in this case, the viscosity profile, will change how this square box looks like. So for example, if we put ourselves a spherical harmonic degree 2, which means 10,000 kilometers in wavelength, and we put ourselves in the middle of the mantle, so for example, around here, what we'll see is that the contribution that we have in the linear viscosity profile, it's larger than the one that we have in here. You see that the color blue, it's much more pronounced. If we choose to be a spherical harmonic degree 10, which is around 1,000 kilometers, we will be around this line here. And if you see, if we look at the same depth that we were before, here we still have a contribution of the surface topography, but in here we will have no contribution. So this tells us that the surface topography, depending which viscosity profile, will change faster or slower.
Excuse me, could you explain what?
Sorry.
harmonics you're talking about?
A spherical harmonic degree is a mathematical way to.
I know what they are, but
Oh.
is it gravity, magnetic, or what is it?
Excuse me, I didn't understand what you said.
It's a topography, but it's just really the long way from topography without any association. Sorry, just the static effects from the static effects. So it's due to the Mantle pushing it. So
Yeah, but when I refer to spherical harmonic degree, in my case, I'm just searching for which wavelength of, if you have an anomaly inside the mantle. Okay. Okay. So here it's just solving the mass and momentum equation, but what we can do is solve it in time. And this is actually the movie that I wanted to show you. So yeah, so I'm presenting you here a standard geodynamic Earth model. And what you see here, it's 4 point of view of the Earth. This standard Earth model, it's the result of solving computationally the mass, momentum, and energy equations, and putting as boundary conditions the surface velocities on top. This implies that the continents will move not at constant velocity far away from each other. So sometimes they will go faster and sometimes they will go slower. So the flow will be dominated by the boundary conditions. The spatial resolution of this model, it's quite high. It's around 8 million grid points, which means a grid point at 30 kilometers in the surface. So for example, from here, Sydney till the Blue Mountains will mean that at least we will have 3 grid points. And such high resolution allow us to model precisely how the properties of the Earth would change and give us, for example, an output as the vertical motion. So I'm just going to run it again so you can see it again. And what I want you to focus is that in different parts of the mantle, so for example, here in the Pacific or under North America, the mantle is different. And even though this is a very simple, well, it's computationally expensive, but it's a simple model that just takes into account the surface velocities, we can see that there's some zero features emerging. So for example, a plume here in the middle of the Pacific, or the slab under Asia creating in here. If you look closely around here, you'll see the Iceland plume arriving. There's also a plume here in the middle of the Atlantic showing up, and there's also subduction zone due to the growth of the Andes or the Himalayas that you can also see in this model. But what does, sorry, so go ahead. 250 plus and minus. So yeah, I actually, yeah, it's a radial, like it's a layered mantle. Exactly. And I can write again just for you to show it again. So the the blue surfaces are represented we call them slabs, and they are the cold downwellings, and the hot upwellings, which are known as plumes, are here represented in red. And yeah, the ISIS. Yeah, well, so what does these models do for us? They actually alert us which are the observations that are necessary to see and to check the validity of these models. The input of these models, as I said before, it's the plate velocities. And as an output, we would get, for example, the vertical motion. So what we want to do now is to find a way to go to observations and see if we can observe vertical motion in the surface of the Earth. Yeah, so let's move to the presentation again. So I present you here something that you probably have seen millions of times, which is the plate tectonic configuration of the Earth. And we can identify, for example, the Pacific plate or the Australian plate or the African plate. And even though this is nothing new and you have seen that, what we can do is take a modern approach and study Earth in a different way. So for example, what we can do is with the position of the continents nowadays, we can plot the spreading rates. The spreading rates are the velocities at which the plates move away from each other. Here, the color scale that you can see, well, what I present you here in color, it's the spreading rates at throughout time. And what you can see is that there's quite a lot of variation. We chose this color scale to highlight mainly the changes in the Atlantic and Indic realm. So purple brownish colors represent very slow velocity. And when we go towards green and bluish, we see that there's faster velocities, because we see that there's a lot of variation, but it's quite hard to read. What we did is extract the profiles throughout the Atlantic and Indic Ocean. In the y-axis, I show you the spreading rate in centimeters per year. And in the x-axis, I show you the time in millions of years. We can go through because there's a lot of different stuff, but for example, we can go here if we focus in the North Atlantic, what we can see is that the spreading rates initiates at around 60 million years with a very high spreading rate, which lasted more or less 10 million years, and then it drops. There's also an iconic observation in the South Atlantic, which is, I put it larger here, which is the bimodality of the spreading rates. What we have is high spreading rates during the Cretaceous, which is more or less between 100 and 80 million years. Then we have a drop in the velocities for 10 million years and an increase again until the Oligocene, which is around 30 million years. This iconic bimodality of the spreading rates have been known for a very long time, and it's nothing new. But what we see in general is that the plate boundary, the spreading rates changes at time scales of tens of millions of years. And a mechanism that has been usually evoked to explain such variations, it's plate boundary forces. So for example, in the North Atlantic, to the changes in stresses in the alpine collision would change the spreading rates, or in the South America, due to the growth of the Andes. But another explanation for such changes is basal forces due to mantle convection. And this is what I explore here in this talk. But mantle convection is very complicated, and sometimes, so what we are taking is a very simpler approach, and what we are using, it's some kind of models that are called Couette and Poisson, which shows they are a simpler way to show flow in the uppermost part of the mantle, which we call the asthenosphere. This view has been popularized over the last decade by Adrian Lenardic in Rice University in Houston. So we have the Couette flow here. This flow is created by a gradient of velocities between the top and the bottom of the layer. The top, in case of the Earth, the top moves, the lithosphere moves and drag the material with this linear profile you see here. This type of flow is mainly driven by the plate tectonics. Then we have the Poisson flow. this plus-oil flow is driven by a pressure gradient within the channel. In this case, you have high pressure on the left and low pressure on the right. And this creates the material to move with this parabola profile with the maximum velocities in the middle. This type of flow is created usually by a plume or a slab transiting through the asthenosphere. And finally, we have the combined flow, which is usually what we encounter, and it's a superposition of both couette and plus-oil. This couette plus-oil flow model makes an explicit prediction on vertical motion. Every time that the basal forces changes, not only the spreading rate has to change, but also the topography must change. So there's an implicit relationship between the spreading rates and the topography changes. But how can we find dynamic to how can we map vertical motion? Well, over the last 10 years, we have become quite good on that. The group in Cambridge has obtained the best residual dynamic topography map of the present day in the oceans and in the whole world actually. And they have more than 2,000 spot measurements of residual bathymetry in the oceanic realm. To extract such a signal in the oceans, what you need to know is the expected depth of the lithosphere and then extract systematically the variations from it. There's a lot of different features in this figure, but what I want you to show, for example, here in Australia, here we have Australia. So there's the Antarctic Australia discordance, which is shown as a negative residual dynamic topography, or we can also go to the other side of the world and go in Iceland, where we see that there's a positive residual dynamic topography. So seeing this process in the oceans gives us an understanding of how this could also affect the continents. So if we go to the continents, what we can do is go to the geological record. So for example, we can have here the geological map of Australia. If we look at this map, me as a geophysicist, I find it very hard to read and identify different geodynamic processes that has happened. And this is because the color scale that it was designed for this map was to highlight maximum changes between sedimentary layers. And probably you have seen this chart at some point, which the colors that you see here are the colors that usually the geological maps use for identifying the different temporal layers. Pinkish, it's represents very old rocks. Then we can go to middle old rocks, which is usually seen as like this brownish, greenish color, and very, very young rocks are represented in yellow. So if we go back again to the Australian geological map, what we can see, for example, is that here in the south, we have very pinkish rocks, very close by to yellow rocks. So we are seeing very old rocks in contact with young rocks. And this can be an indication that there's actually some mantle process or some processes that has happened. But then the question that we have is, how is vertical motion reflected in the geological record? Well, as I said at the beginning, mantle convection deflects the surface of the Earth. And this process is quite complicated, but I have a simple sketch here to see how this deflection affects also the sedimentary record. And this method it was published by Friedrich et al. A few years back. So what we have here, it's a rising plume. And here I have two stratigraphic columns, one in the center and one in the far fields. And here on the right, I amplified the stratigraphic column so we can see how the sedimentation goes. In this stage, the plume doesn't interact with the surface, so both stratigraphic columns will sediment the same. In the next one, the plume interacts with the surface, creating in column A a non-depositional environment or an erosional environment, and avoiding that the sedimentation occurs in column A. Column B will still sediment. Here, in the next sedimentary layer, will only sediment in the far fields. So column B will have sedimentation, but column A will have a gap in time. And this is well known in geology as hiatus. Finally, when the plume flattens and sedimentation resumes everywhere, column B will have the expected sedimentation. Column A will have a gap in time, so a hiatus. So that's what we did, and we mapped all these hiatuses in the geological record. So how do we see that in a map view? So when we have 3 layers, 1, 2, 3, in a map view, if they are perfectly aligned, we will only see the youngest one. But in case that there's for some reason they are shifted, in the map view, we will see all 3 layers, and the contact between these 3 layers, it's going to be called a conformable contact. This would be the case of column B. If we go to column A and layer 2 is missing, what we have in the map view is that we'll have directly a contact between layer 1 and layer 3 there. And this contact we'll call unconformable contact. And as you can see, we already assigned colors to both contacts. Blue is going to be representative of conformable contact, and red is going to be representative of an unconformable contact. So let's go and try to having here a schematic geological map. How do we map this? Okay, so let's grab the layer T1 and see what is in contact in this map. If we look in here, the layer T1 is in contact directly with T3. So there's a layer missing. So this is going to be mapped as an unconformable contact. If we go here on the left, we see that the layer T1 is in contact with T2. So this is going to be mapped as a conformable contact. But because we want to go to the extra length and map exactly where there is layer T2 and where there is not layer T2, what we're going to map is also the contour of the layer T2. And this will give our maps as a proxy of what happened to the previous layer or not. If we do that to all the sedimentary layers we have in the geological map, and I don't know why there's, sorry about that. We do that on all the, we'll get, it's a group of time windows with information of what happened to the previous time step. So for example, in here in base of T1, what we'll see is that the layer T2 is not there, but the layer T2, it is there. So if we do that and we put all these in a regularized grid and apply a spherical harmonics expansion, what we'll get is the following surfaces. So what I show you here, it's the base hiatus maps centered in Atlantic, or the BHS also. We have here 8 time windows separated in geological time series, which is tens of millions of years. We chose the base of the Lower Cretaceous as our oldest time step because it corresponds to 1 transit time of the Earth mantle. A transit time is the time for a mantle overturn, and usually it's between 100 to 150 million years. Blue means a no hiatus, so it means that the previous layer is there. So for example, if we take the base of the Lower Cretaceous, everywhere we see blue means the Upper Jurassic is there. Red means a hiatus, so that means that the previous layer is not there. So if we take again the base of the Lower Cretaceous, it means that the Upper Jurassic is not there. And white is the absence of the previous and the previous before. It's the absence of the series and the series before. So in case of the Lower Cretaceous, when you see white, it means that there is no Lower Cretaceous nor Upper Cretaceous. The black dots that you see in this map are the current location of Iceland, Canaries, Tristan, and Afar plumes. We take this map as a proxy of vertical motion that the area has undergone. So in other words, it's an indication of what happened to the previous time step. For us, this is a key result, and it will have a significant impact in how geodynamics develops in the future. The main observation that we see is that the proxy of vertical motion seems to systematically change at each time step. So what I'm saying is that each map looks different. And note that this time, it's much shorter than the mantle transit time, which would be the time at which we would expect changes in topography. And this is an indication of clear properties of specific properties of the Earth's mantle. So now let's look at what the maps tell us. For example, if we start in the base of the Lower Cretaceous, what we can see is that Africa and South America mainly has a hiatus, which is an indication of high topography of the Upper Jurassic. This precedes the arrival of the Tristan plume at 133 million years ago. If we go to the next time window, what we see is that most of the continents now, they have sedimentation, they have a no hiatus, which is an indication of a lower topography. If we continue studying these surfaces, we see that the main surface, hiatus surface that we see, it's in the base of the Miocene. But I am a global geodynamicist, so what we did is we extracted these surfaces for America, North and South, Europe, Africa, and Australia. And what we see also is that each map, again, looks different, and each continent has a different evolution. So for example, we can look at Europe, and if we look here at the base of Eocene, we can see that Europe is mainly red, which is an indication of high topography of the Paleocene. And this is, again, precedes the arrival of the Iceland plume. Because we are here in Australia, we can also take a look at Australia. And for example, what we can see is that we have a change in topography in the base of Paleocene. We have mainly the high topography in the west, but in the next time window, it shows lower topography in the east and high topography in the west. But if you remember at the beginning of my talk, I told you that these models gives us a relationship between how the spreading rate changes and how the dynamic topography changes. So what we can do is take both observables and look at them together and compare them. So here, complicated slide, let me just walk you through it, please. So if you remember at the beginning, I show you how the, I showed you the bimodal spreading rates of the South Atlantic, which are here in the lower row. I also explained you 5 minutes ago how the base hiatus maps look like. And if you remember, red means a hiatus and it's a proxy for high topography, and blue means a no hiatus and means it's a proxy for lower topography. But these maps are quite qualitative. So what we can do is try to find a quantitative way of quantify how this each continent is elevated. So what we did is we took the hiatus and blank surfaces and we add them together and normalize them in the size of the continent to get these curves that you see in here to quantify the proxy of elevation. The solid line you see here, it's Africa. It's the continent of Africa, and the dashed line you see in this first plot, it represents the continent of South America. If we look at it, we can see that in the Upper Cretaceous, they were both high, and in the Lower Cretaceous, they had subsidence. Then the curves diverge here in the Paleocene until the Oligocene. In geodynamics, it's usually believed that South America went away from a high topography in Africa, and then it subsided all the way through the present day. But our maps actually show something different. But yeah, also because Africa is a very big continent, what we did is separate the north and the south part. And this is what you see in the middle plot. The dotted line, it represents North Africa, and the dashed line represents the South Africa. And if what we see is that, for example, in the Upper Cretaceous, we have a divergence of how North and South Africa behave, having here a higher elevation in South Africa. And if we now look at the spreading rates variation, and we remember what we said, if we have high topography, this will generate basal stresses that will transmit throughout the lithosphere and can generate a change in the spreading rates. And this is in the base of low Cretaceous, we have high topography, which is followed by an increase of, by the onset of spreading rates in the South Atlantic. We can also see that here in the Paleocene, we have South America with a high proxy elevation, which coincides with the speed up of spreading rates in the South Atlantic, culminating in the Oligocene. And these observations of time variation of sedimentation have been found by others. There's actually a study, an IODP study by Barker, that shows that in the early Eocene, there's aerial subexposure on of the Rio Grande rise, located more or less in this place. But since we are here, we can also look at Australia. So here we have again the base hiatus maps on top. On the lower part, I show you the spreading rates. The dotted line shows the spreading rates in the low Howe rise in the East Australia, and the solid and dashed lines show the spreading rates between Antarctica and Australia. In the middle, I show you again the proxy of elevation. The solid line, represents the Australia continent. The dashed line represents Western Australia, which coincides with the political boundary, and the rest we considered is Australia. And if we look at it, what we can see is that we have high topography of Australia in general in the upper Cretaceous, followed by a high in Western Australia, but relatively lower in the rest of Australia in the east. And if we look at the spreading rates, what we see is that actually we have a highs, like when we have this high in topography in Australia, the spreading rates in the east initiated and continued through. And finally, in here in the Paleocene, when we see the Western Australia also elevated, then after that we have the onset of spreading between Antarctica and Australia. And in a recent paper that we submitted, we attribute this change to one of the pulses of the Kerguelen plume. And I'm almost at the end of my talk, but before I told you about this quad Poiseuille flow model, and I want you to show them to you in a appropriate geometry, so in a spherical geometry. So what I show you here, this is the quad flow, and we extracted from the plate velocities at 55 million years and 133 million years. The second column is the Poiseuille flow. So, and it simulates how would be the flow in the asthenosphere when we have an injection of a plume. The combined flow, which for some reason there's no arrows in here, which there should be, maybe formatting problems. The combined flow, it's the sum between the quad and the Poiseuille. You can see it here, at least in the Tristan. And the main point of this slide, it's actually this last column. This last column in orange, you can see the area affected by the Poiseuille flow. So it's the areas that the Poiseuille flow dominates the quad. And if you see the blue line, this is when we consider the plume strength, half of the one that we took here. And you can see it here for the Iceland plume and for the Tristan plume. If we take the case of the Iceland plume, we see that the majority of Europe would be affected by the arrival of Iceland. And these surfaces are in the range of 10,000 kilometers squared, which are similar sizes of what we find in our base hiatus surfaces. But yeah, so now that we've seen all these observations, what we could do is go back to the models. And as you remember, I showed you that model before. And the good thing is that this model predicts the vertical motion. So with our proxy of elevation maps, at some point we would be able to test if the predictions of these models make, to validate our model. But now it's possible also to invert these models back in time and get a trajectory flow of how the particle has evolved through time. And actually, this is going to be a further step in my PhD. So to finalize the talk, I just want to do some highlights. Dynamic topography is a crucial geodynamic observable. The base hiatus maps that I present you here are a proxy for dynamic topography. What we saw is that they vary at time scale of geological series, which indicates a rapid upper mantle flow and is consistent with the presence of a weak asthenosphere. We see an uplift prior to the change of horizontal motion, and we can link it to the rise of a plume through the mantle. And finally, a disclaimer is that the geodynamicists need to embrace geological datasets in order to advance in our understanding of geodynamic processes in the Earth. Thank you very much. Any questions are welcome.
Thank you. That was a very interesting talk, and I just can't imagine how much computer power you need to get to that stage. Those 3D models would have been a lot of work.
Yeah, those models run in a supercomputer.
Having done my geological training before plate tectonics came into common use, I have a question about plumes.
Yeah, go ahead.
Are they thermal waves, or are they actually magma material coming up, or thermal waves that get close to the surface where the pressures are lower and they turn into more magmatic flow? My thoughts are that they possibly start off as a thermal wave passing through the mantle to then provide that expansion. Is that the theory? Correct me as long. It's an uneducated question.
So if you remember the movie, the video that I showed, this is actually, we see, like, we took an isosurface, but basically it's hot material rising through. And what I would say, it's like it's the material that it's hot, and it just, because it's less dense than the rest of it, it just goes through. And
So
Convection over conduction.
yes.
yeah.
Okay.
Sorry.
The other question was, who did all the work in finding and doing the mapping for the hiatus sections? That was not trivial to cover the whole world. Was that your job, or did you manage to collect a lot of that?
Partly. So that's a collaboration with a lot of people. So yeah, so America, so North and South America, Europe, and Australia, where the majority of the data comes from the digital geological map that is available online. So we have a program that runs through it. Africa and actually Australia is enhanced with reports of stratigraphic columns, regional maps, to make it like that somebody went through, sit down very long hours and extracted all this data.
Seems like a gigantic project to me.
It's a lots of effort, and Sara Carena spent a lot of time actually working through. We had the computational power through, and because we have the geological maps online now, it's much easier for us to run a program through instead of just sitting down for a while.
Well done.
Thank you.
Yes, thanks for a very interesting talk. For that hiatus map you did of Australia, at what level were you trying to create these discontinuities in the sedimentation? Is it just the level of the Great Artesian Basin versus the material that sits beneath, or are you trying to, is it just at a gross level you're working on this hiatus mapping?
Yeah, so the hiatus, it's defined by the geological series. So so the temporal resolution that the chronostratigraphic chart gives us. So well, you all know that.
Yeah.
And
Well, let me ask the question another way.
Yeah.
Is the hiatus map for Eastern Australia just the Cretaceous Great Artesian Basin sitting on older material? Is it just the one hiatus, or do you have many hiatus
You mean that it's
in Eastern
longer?
Australia?
Yeah, like actually, it's not just one series. It expands throughout more than one. That's also why you see blank regions for longer time than just one series. We have the.
Okay, well, let me
I'm sorry.
following on from that. This is only good for material that's been accumulated since as old as the ocean floors go. So it doesn't go, you can't go beyond the Cretaceous because we don't have any ocean. We don't know spreading rates before the Cretaceous. So go on. Yeah. Well, that's what I'm. So
Speculation.
yeah. But if you need to know the velocities of the plates, do you know velocities of the plates before the oldest seafloor material that's presently around?
You can take it. Probably you're more educated than I
No,
am.
that's my paper, not yours. And the short answer is they're proxies for it, but I'll talk to you about after.
Let's see. What we use mainly it's data from like geological information from the continents, and the continents can go farther back than just the Cretaceous. For now, we just limit it until the Cretaceous, but yeah.
Sure. And can I ask us one final question? The lateral resolution that you have in these models, I'm interested in the Great Dividing Range in Eastern Australia. So we have an elevated Great Dividing Range, but we don't have an elevated coastal plain. Is your model adequate to separate that sort of those changes in vertical motion, or are we looking at a grander scale?
When you say model, you mean these surfaces you see here?
Yes.
Because this is not a model. This is just extracting information from the geological record. So we did not model anything. The only thing we did is to smooth the surfaces, but that's only data from the geological map. We did not model anything from it. We just compared the observations.
Thank you.
I just want to clarify one thing. So your hiatus and non-hiatus is based solely on what's at the surface. Is that correct?
Yes, for the majority of the continents, but Australia, for example, has been enhanced with the subsurface information.
Okay, thank you.
Derail things. You drew a really nice bow between the observations of unconformities and then through to your dynamic topography, and then all the way to spreading rates, which sort of that flows nicely. But I wonder if it's kind of a closed loop in some ways, in that your spreading rates then impacts your sea level. You get regressions and transgressions depending on the spreading rate, and there's a classic transgression during the Cretaceous associated with fast spreading, and that would then impact whether or not you're seeing deposition or erosion on a given site. I just wonder how, if you could, deconvolve those signals.
So yeah, that's a very actually good question. The maps obviously contain, for example, sea level variations, because if you have a high sea level, you'll have much more sedimentation. And you can, for example, the only way that we can have to deconvolve this, it's study how the whole continents look like, and if you study them separately. I don't have a figure in here, but I have a figure in one of the papers where we actually compared how the hiatus surfaces change globally and how it changed for each continent. And for example, for the base of the Miocene, you can see that the majority of the continents are red, which means that there's much more or less sedimentation of the Oligocene. But we relate that to a drop in sea level because of the glaciation of Antarctica.
So by working out what the mean is at any given time, what you're basically saying is you could reconstruct an independent measure of your global sea level curve.
Mm. I am actually not sure we could do that yet.
I reckon you could.
Okay.
Just, and then the last thing was the elastic flexure of a plate
Mhm.
due to dynamic topography effects. Australia, you know, during the period when it had an inland sea, seemed to tilt quite a bit over the Antarctic discordance. Is there any way, it's sort of, I mean, this is a global scale, so it's very much a larger scale than the elastic plate effects, but is there any way to consider those? Are those proxied in any form, or is it sort of second level detail still?
Like we did not look at it at all. It could be actually maybe a further step to take into account, and just especially when we look at specific continents. But yeah, like we have not thought much. I have not thought much about it yet. Thanks.